ketoacidosis in non-compliant type 1 diabetic. So Jessica is a 25-year-old female that presents to the ER with fruity breath, nausea and vomiting, as well as confusion. She also shows up to the ER with some classic symptoms associated with diabetes. So she's got increased urination, increased thirst, as well as increased appetite despite her signs of malnutrition. That BMI is extremely low. Her A1C is super elevated, and the electrolyte panel shows that she's hyponatremic as well as hypokalemic. Any pH value that's going to be below 7.3 is characteristic of diabetic ketoacidosis, and her plasma glucose actually indicates that she's in a severe state of that. Her chart history indicates that she was early diagnosed a type 1 diabetic, and this is the 4th time she presents to the ER with these same signs and symptoms, and each time she's been diagnosed with DKA. She's also endured a previous psych admit. The patient's known to withhold her insulin, and she does this in order to manipulate her weight. So we know her diagnoses here. So she's got DKA, the side effects of excess ketones being present in her urine, and she's also dealing with some low blood pH. That would be a result of the DKA. The patient also has diabulimia, so she's deliberately giving herself less insulin than needed, and maybe she stopped giving it altogether in order to lose weight. And this is typically found in type 1 diabetics. We do know that she has type 1 diabetes, so she's not producing enough insulin in the pancreas, so then there's a reduced uptake of the glucose from blood into the tissues. This should and would be managed well with daily insulin injections. So we know that all this is associated with the metabolic pathway of glycolysis. So one glucose molecule is actually a 6-carbon molecule, and it's broken into 2 pyruvates, so 2 molecules of 3 carbon molecules. And this is actually going to yield 2 ATP as well as 2 NADH molecules. Glycolysis is able to function without oxygen, and it takes place in the cytosol of the cell. So here are the stages of glycolysis. So stage 1, we have ATP investment. That's going to be the first half of the process. So step 1, glucose is phosphorylated into glucose 6-phosphate by hexokinase, which actually breaks down the glucose into the muscle. In the muscle. This can also be done by glucokinase, but that would be done in the pancreas and the liver. So step 2, phosphoglucoisomerase is the enzyme that's going to rearrange glucose 6-phosphate into fructose 6-phosphate. So those two are isomers of each other. Step 3, so fructose 6-phosphate is phosphorylated into fructose 1,6-bisphosphate. It brings us to step 4. So F1,6BP is split by aldolase into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. These are both 3-carbon molecules and isomers of each other as well. Step 5, DHAP is converted into GAP by triose phosphate isomerase. So now we're at the second stage. This is going to be the energy payoff phase of glycolysis, and this is the second half. So step 6, GAP is converted to 1,3-bisphosphoglycerate by glyceraldehyde 3-phosphate dehydrogenase. In step 7, the phosphoglycerate kinase converts the 1,3-BPG into 3-phosphoglycerate. In step 8, then that 3-phosphoglycerate is converted into 2-phosphoglycerate by phosphoglycerate mutase. Step 9, enolase converts that phosphoenopyruvate, and which is then catalyzed by the pyruvate kinase to form pyruvate. So here we are. We have some results of all of this. So the patient's actually dealing with hyperglycemia. There's too much sugar in the blood, and it's causing a decrease in insulin levels, which then will result in ketoacidosis. This happens because the patient just hasn't received enough insulin, and ketones are forming, which is giving her some acidic blood. And now insulin is another thing that this brings us to. Insulin is going to be responsible for regulating glucose. So insulin decreases blood glucose levels by increasing glycogenesis. Glucose eventually gets into the cell by help of an insulin receptor, and when the glucose enters, it may undergo glycolysis, or it may even undergo glycogenesis. So the following steps are highly regulated, they're irreversible, and they have large negative free energy change. So step 1, hexokinase. So we know that some ATP is made here. There's a decent drop in energy. In step 3, there's significant drops. So this is going to be the most important regulation step because it controls the flux of glycolysis in the muscle. And step 10 is not the best. It's not the best regulator because it's at the end of the cycle and it really doesn't have time to do anything or do anything too significant. So the hormones that are affecting the blood glucose here. So insulin, we know that it's going to decrease the blood glucose by increasing the glycogen production. With an increase in glycogen, there's also an increase in the blood glucose. And this is going to be breaking down the glycogen. So all these other hormones here, they're going to increase the blood glucose as well. So in regards to the metabolic profile, this is how it's going to affect the other organs. So in the brain, the hypothalamic neurons are going to be for nutrient and glucose sensing, to see just kind of where we stand, how much we have, what else do we need. And in the liver, glycolysis controls the liver glucose production. So just what we were talking about in class, the before and after breakfast, before breakfast, patient's going to be low in insulin, high glucagon, and low blood glucose. But if we're comparing this to the patient's going to have, decreased insulin because she's restricting. She's going to have high glucagon levels, but she's actually hyperglycemic. The hyperglycemia should be suppressing the glucagon levels in a non-diabetic. The picture here is just comparing different rates of glycolysis between type 1 and type 2 diabetics. Glycolysis rates are decreased in all tissues mentioned for the type 1 diabetic. So in regard to exercise and blood glucose levels, initially there's going to be an increase in blood glucose, but then after a few minutes of exercise, the exercising muscle actually increases insulin sensitivity, which promotes the glucose uptake and lowers the blood glucose. So the type 1 diabetes metabolism status. So glycolysis is going to regulate the secretion of insulin. However, this process malfunctions with a lack of insulin. Without any insulin, we're going to be leading to no glucose being converted to energy, which leads to glucagon production, which increases the blood glucose. So in conclusion, diabetics are already going to be at risk for developing DKA, especially type 1 diabetics, but Jessica's really bringing this additional danger upon herself. She's purposefully non-compliant with her insulin because she's trying to lose weight, but this is actually going to do the opposite for her. These recurrent DKA episodes, or even just having increased blood glucose levels for so long, will lead to weight gain. And in regard to treatment, we're looking at giving her some more fluids, giving her some more electrolytes. She's got to be consistent with the insulin. The fluids and electrolytes are actually we need to increase the sodium that we know was depleted before, as well as the potassium that was depleted when she did arrive to the ER. All right, and then here are my references, and that's it. Thank you.